Welcome to all of you, dear students, Advanced Mechanics, Mathematics Honors, University of Calcutta, Semester 6 under CBCS, Unit 1.2, Constraint. First, we discuss about generalized coordinates. The smallest possible number of variables to describe the configuration of a system are called generalized coordinates. Thus, the name of generalized coordinates is given to a set of independent coordinates sufficient in number to describe completely the state of configuration of a dynamical system. So, uh, this must be independent coordinates. If n is the total number of generalized coordinates, then these can be written as q1, q2, qn, this. Some examples. For a particle constrained to move on the circumference of a circle, only one generalized coordinate q1 equal to theta is enough to describe the motion. Second example, for a particle moving on the surface of a sphere, we need two generalized coordinates q1 equal to theta, q2 equal to phi for describing the motion. Some important remarks about generalized coordinates. First, the generalized coordinates do not necessarily belong to any conventional coordinate system like Cartesian coordinate system, polar coordinate system, or spherical coordinate system, etc. etc. Number two, the generalized coordinates can be any curvilinear coordinates, dimensionless parameters such as angles, distance, or their combinations. So these Q1 and Q2 up to Qn may be say angles or distance or others, dimensionless parameters. Number three, for holonomic system, first what is holonomic? We discuss later this. The number of generalized coordinates is exactly equal to the number of degrees of freedom of the system. Already we have discussed what is the degrees of freedom of a system. So for only holonomic system, degrees of freedom, number of degrees of freedom equal to the generalized coordinates. For a system of capital N particles having k holonomic constraints, the total number of generalized coordinates is 3n minus k, that is the number of degrees of freedom. But for non-holonomic system with capital N particles, k holonomic and k dash non-holonomic constraints, the number of degrees of freedom is equal to 3n minus k dash. And the number of generalized coordinates is 3n minus k. Obviously, for non-holonomic system, degrees of freedom always less than the number of generalized coordinates. And these generalized coordinates for this non-holonomic system are called quasi-generalized coordinates. Generalized velocity. Total time derivative, that is ddt, of any generalized coordinate is called generalized velocity. It is denoted by qi dot. This dot means ddt. Here qi dot equal to ddt of qi, I runs from 1 to n. This small n is the number of generalized coordinates, capital N is the number of particles of a system. In configuration space, the set of all generalized coordinates q1, q2, qn span an n-dimensional space Rn called configuration space of the system. At any given time t, the system is located at some point in its configuration space. So the time evolution of the system is represented by a definite trajectory in its configuration space. Now, what is constraint? Often, the motion of a particle or system of particles is restricted by one or more conditions. The limitation on the motion of a system are called constraints, and the motion is said to be constraint motion. For example, a particle like bead moves on a wire or on a surface, plane or curved surface, then constraints required that describe the position of that particle on the wire and on the surface. Next question, describe the basic properties of constraint forces. First, the constraint forces are elastic in nature and appear at the surface of contact. They arise because the motion defined by the external applied force is hindered by the contact. Number two, the constraint forces are so strong that they rarely allow the body to deviate from a prescribed path or surface. This prescribed path or surface is called a constraint. The scalar equations that describes the surface of constraint are called constraint equations. Number three, the sole effect of constraint force is to keep the constraint relation satisfied. Next question, classify the different types of constraint. Constraints are classified into different types as follows. First, we can classify the constraint only time dependent or independent. Number two, integrable or non-integrable. Number three, conservative or non-conservative. And number four, algebraic equation or inequalities. So, this time dependent or independent may be classified into two types. Scleronomic constant relations do not explicitly depend on time. Then this constant is called scleronomic constant. And number B, rehonomic constant relation depend on explicitly on time. Then this constant is of type rehonomic. Integrable, non-integrable constraint relations are or can be made independent of velocities. Then this constant is called holonomic constraint. And non-holonomic constraint relations are not holonomic, means non-holonomic constraint. Conservative, total mechanical energy of a system is conserved while performing the constant motion. Constant forces do not do any work. This conservative force, conservative constraint. And dissipative, constant forces do work and total mechanical energy is not conserved. Algebraic equation or inequalities is first bilateral. At any point of the constraint surface, both forward and backward motions are possible. Constraint relations are in the form of equations. Unilateral, at some point no forward motion is possible. Constraint relations are expressed in the form of inequalities. Next, describe about limitations of Newton's laws for solving dynamical problems. This classical mechanics, this Newton's law. Newton's law are valid only in inertial frames. For non-inertial frames, such as a frame attached to Earth rotating with it around its axis of rotation, or the motion of any object with respect to Earth, is a motion in non-inertial frame of reference. A transformed version of Newton's equation of motions obtained in which pseudo forces like Coriolis forces or centrifugal forces enter into the equations. So Newton's law valid for inertial frame of reference, either rest or moving with constant uniform velocities. But non-inertial frame is with accelerated velocities or rotating these non-inertial frames. Newton has not given any description for calculating forces of constraints. Hence, in absence of the knowledge of the total force, Newton's second law in its differential form cannot be formulated, let alone finding a solution to dynamical problems involving the constant forces. And so, we now study advanced mechanics. Question, explain about work done by constraint forces. Usually, the constraint forces act in a direction perpendicular to the surface of constraint at every point on it. While the motion of the object is parallel to the surface, at every point. At every point, in such cases, the work done by constant forces is zero. These constraints are termed as workless and may be called as ideal constant. For example, when a particle slides on a frictionless horizontal surface, the force of constraint is normal to the surface. What is the force of constraint here? The reaction force on the particle, this frictionless surface. But there are examples for constant forces that do work. Example, when a body slides on a frictional surface, the frictional force due to sliding does work for real displacement. Other example is the rheodomic constant, for which the constant force tension T vector need not act perpendicular to the real displacement delta r vector. For a bob of pendulum with variable string length L, this L depending on time t, this variable length, where this T vector dot delta are not equal to 0, that is work done by T vector is non-zero. This is the variable length, this L and this L dash, this is the point of suspension, and this distance is delta r at this time position at time t, and this time is T dash, is delta. Define holonomic and non-holonomic constants with examples. What is holonomic constants? Holonomic constants, this if they are geometrical or integrable kinematical or their corresponding equations do not contain derivatives of the coordinates of the points in the system. For holonomic constant or integrable constant, the constant equation is in the form fj q1, q2, qn, comma t. These qis are the generalized coordinates and t with the time. This j runs from 1 to up to k. K is less than n number of generalized coordinates. For jth constants, this equivalent form is del qy fj dqy summation over I is equal to 1 to n equal to 0, as it is integrable. So this is the function with generalized coordinates and time. This equals to 0. This type of this holonomic constant of type. Example, in case of motion of rigid body, the distance between any two particles of the body remains constant and do not change with time. If Ri vector and Rj vector are the position of vectors of the ith and jth particles, then the distance between them can be expressed by modulus of Ri vector minus Rj vector equal to Cij. This is equal to constant. Say, if xi, yi, zi with the coordinates and xj, yj, zj, the Cartesian coordinates of the two particles with position vector Ri vector and Rj vector, then the constant becomes xi minus xz whole square plus yi minus yz whole square plus zj minus zi minus zz whole square equal to Cij square. The constant is holonomic and scleronomic conservative bilateral also here. And note this term holonomic comes from the word holos, which means integer in Greek and whole or integrable in Latin languages. This is the holonomic generation of the term holonomic. And non-holonomic, a system is said to be non-holonomic if it corresponds to non-integrable differential equations of the constants. Such constants can be expressed in the form of the equation 1, cannot be expressed in the form of the equation 1, this f q1, q2, qn, comma t equal to 0. So for these non-holonomic constants, we can express this. There are two types in these categories. Equation involving velocities. This is generalized coordinates q1, q2, qn, and the generalized velocities q1 dot q2 dot qn dot comma t equals to 0, but cannot be reduced to holonomic form. And there's inequalities, that is this f q1, q2, qn, comma t, this less than or greater than equal to 0. So this is the inequalities type is also non-holonomic. And in both holonomic or non-holonomic cases, time t may or may not be present explicitly. An example of this, suppose a spherical ball is rolling on a plane without sliding. The velocity v vector of any point P in the rolling body is given by V vector equal to V0 vector plus omega vector cross R vector, where V0 vector is the velocity of the center of mass and R vector is measured from the center of mass to the point P, and omega vector is the angular velocity. The constraint equation is then given by V vector equal to V0 vector minus R vector omega vector cross n cap equals to 0 vector at the contact. Since this R vector equal to minus R n cap vector. N cap is the unit vector along the outer normal to the plane, and R is the radius of the sphere. And for a sphere, this constraint is non-integrable because omega vector is generally not expressible in the form of the total time derivatives of any single coordinate. Thus, the constraint is non-holonomic. And prove that this constant q1 dot plus q2 into q2 dot plus q1 q2 dot plus q2 into q1 dot equal to k each holonomic type constants. It may so happen that the constant relations contains velocities qi dot, but can be integrated with respect to time t so that the resulting relation is made free from velocities. So this the holonomic constants is free from the velocities qi dot. Here the generalized coordinates q1 to qn and time t may or may not be appear here, but no velocities generalized velocities q1 dot, q2 dot and qn dot here. But in this equation, here q1 dot, q2 dot appears here. But we can remove this. The given constant relation can be written as this first half of ddt of q1 square plus q2 square, because ddt is this, that is 2 q1 into q1 dot plus 2 q2 into q2 dot and half, so cancel 2, and plus ddt of q1 q2, that is q1 into q2 dot plus q2 into q1 dot, these terms, this is equal to k. So integrating this integrable, this q1 square plus q2 square into 2 into q1 q2 is equal to 2 kt plus c. C is arbitrary integrating constant. So q1 plus q2 whole square equal to twice kt plus c. So these only two generalized coordinates. There are two generalized coordinates q1 and q2. No generalized velocities here. So these constants, although they are present here q1 dot, q2 dot, q1 dot, but these are holonomic. This is a holonomic constant. Next example: each y z minus 2x plus y bracket x dot plus x z minus 2y plus x bracket y dot plus x y z dot equal to 0 is holonomic constant relation. And so this is the first we write this definition of this holonomic. qi dot generalized velocities appear here, but resulting relation is made from free of these generalized velocities. These equations can be written as this 1 plus z x y dot plus 1 plus z x dot y plus z dot x y equal to 2x x dot plus 2y y dot. And this can be the derivative of 1 plus z x y. So this 1 plus z x y dot plus 1 plus z x dot y from this, and this xy into z dot. So left hand side can be written as this form, and right hand side can be the derivative of x square plus y square. And integrating we get 1 plus z xy equal to x square plus y square plus c. C is an integrating constant. So the constant is holonomic as it is free from the generalized velocities. These are holonomic constants. In the following cases, discuss about the constants. First, rigid body. A rigid body is the scleronomic, holonomic, bilateral, and conservative constant. And deformable bodies: rheonomic, holonomic, bilateral, dissipative, non-conservative. Number 3, simple pendulum with rigid support is scleronomic, holonomic, bilateral, conservative. Number 4, pendulum with variable length, rheonomic, holonomic, bilateral, dissipative. Number 5, spherical container of fixed radius are filled with gas, scleronomic, holonomic, conservative, and unilateral. Number 6, an expanding or contracting spherical container of gas, rheonomic, holonomic, unilateral, dissipative. Number 7, a simple pendulum with its bob sliding on a circular track, dissipative. Number 8, rolling without sliding of a sphere, conservative, non-hologramic. Rolling without sliding of a cylinder, conservative, hologramic. Number 10, particle on the surface of a solid sphere, sclerodermic, hologramic, unilateral. And number 11, sliding of a bead on a wire rotating uniformly about z-axis. This is rheonomic. And last 12, a body on a smooth inclined and horizontal plane. This is the sclerodermic and conservative. Thank you for watching this video.